from lunch. I am Farhan Hasan. I'm a postdoc at Space Telescope, and it's great to be back here. It's my 4th year in a row, but first as a postdoc. It's been fantastic so far. Thank you to all of you, to all the organizers for putting together another really fun event. I'm excited to kick off the Cosmic Web session, but I will specifically talk about what role the Cosmic Web may play in the emergence of galactic morphologies, as well as what we can learn through upcoming missions such as the Nancy Grace Roman Space Telescope. Not sure why this is. Okay. All right. So this is, I think we all know, the modern picture of galaxy evolution. The key point is that galaxies are a consequence of the matter flows across different scales of the cosmic ecosystem. And this really begins at the cosmic web scale, the super megaparsec scale structure we call the cosmic web, which is dominated by these things we call filaments, which channel mass and angular momentum into dark matter halos, which then propagate down into galaxies. So the broad strokes picture is clear, but what's not so clear are the details, right? So the thing I will focus on for the first part of my talk is addressing this question, how accretion from the cosmic web, which really is a consequence of the large-scale tidal field and flows from the large scale, how that results in the observed diversity and complexity of galactic morphologies into the prolates and the disks and the spheroids and things that spin fast, spin slow, etc. But this will be from a cosmological simulation perspective. The second part of my talk, I will attempt to bridge these predictions with observations as will be enabled by upcoming surveys. I think we can appreciate that we live in a sort of golden age of cosmic web studies thanks to these amazing observatories on the ground and in space, which will give us these large wide field galaxy surveys that can allow you to trace or reconstruct the cosmic web structure at early times for the first time, really, at redshifts 1 and above. Roman holds a special place in this regard. It's scheduled for launch a little over a year from now, fingers crossed. And it will not only have a really large field of view with high sensitivity, but also Hubble-like imaging resolution. So imagine a survey like 3D HST or candles over 100 times the field of view. Such endeavors can really, help us understand a lot about how cosmic web accretion literally shapes galaxies. Okay, so the technique that we've been using, me and my collaborators, to identify the cosmic web from galaxy surveys is called Monte Carlo Fisher Machine, or MCPM. And this was actually developed right here at UC Santa Cruz several years ago. The idea is that you're mimicking the growth patterns of the biological slime mold organism, right? So, and the slime mold treats galaxies as food sources, right? So from nothing but the positions and masses of galaxies, you get pretty good estimates of the cosmic matter density field. We've recently shown that when you integrate the slime mold density field into the very widely used dispersed structure identification framework, which I think many of us here are familiar with, this actually helps improve the cosmic structure identification relative to the standard Delaunay tessellation-based density field. And so this is our application for TNG 100. Recently, we've applied this for TNG 50 as well, which is, smaller volume but much higher resolution. And the zoom in sort of shows the filaments, the curves near the galaxies, which are little dots representing different types of galaxies. Okay, so the first thing we look at is the alignment signal between galaxy major axes, okay, and the direction of the nearest cosmic filament. And so this angle, the cosine of this angle is 1 if galaxies and filaments are completely aligned, and 0 if they're completely misaligned or perpendicular. And here is the evolution of this median angle with redshift for the alignment between stars and filaments on the left, and for the alignment between dark matter halos and filaments in the middle. The middle panel also shows two different scales. The dashed lines correspond to outer halo scales, and solid lines correspond to inner halo or sort of galactic scales, right? So there are two main takeaways here, which both show that alignment decreases with time, so with decreasing redshift, and with distance towards the galactic center, right? So you have less alignment as you get closer to galaxies and inner dark matter halos. This is to say that signatures of early angular momentum acquisition from the cosmic web are washed away as time goes by, and as you get closer to galaxies where more baryonic processes such as star formation and stellar feedback take hold. Also, you'll note that prolate halos appear to be the most aligned with filaments at any given time. All right, now for the shape fractions. These are fractions of dark matter halos that are prolate, and I'll also show this for stars later. The prolate fraction of dark matter halos, that's the color coding, as a function of stellar mass on the horizontal axis and the density of the nearest filament on the vertical axis, okay, at different redshifts. You can immediately notice that there's a pretty strong mass and redshift trend. There's very few prolates at lower redshifts, and there's very few prolates at higher masses, right? Now, this is TNG 50, and this is TNG 50 dark. Repeating this experiment with a completely dark matter only version of the same simulation, you can see the trend, the mass trend has reversed, right? Fewer prolates are actually now found in this DM-only universe at lower masses, and more prolates are found at higher masses. So evidently, cosmological accretion under the action of purely gravity forms more prolate structures, right? It's baryonic feedback, or baryonic mechanisms that are responsible for the formation of things we're more familiar with, like disks. Now, we also noticed sort of a filament dependence, but it was not evident in the plot I showed before. So what we did next is we removed the mass dependence. Okay, so this is at fixed stellar mass. Is there a residual dependence of the filament density on the prolate fraction, right? So this shows this residual prolate fraction at fixed mass as a function of the filament line density, where the prolate fraction is measured for stars and for dark matter at the same scale, and this is shown for different redshifts by the different colors. Well, you can see that at fixed mass, low density filaments are conducive to forming prolate structures. High density filaments have fewer prolate structures. We repeated this experiment with the stellar spin. So this is the specific angular momentum of stars at fixed mass. So you see a residual dependence of filament density on the filament density on the stellar spin as well, such that at higher filament densities you have stars that spin faster. You have higher stellar spin. This, of course, decreases with time, such that by redshift 0 the effect almost disappears. And so here is sort of my cartoon, my attempt at making like a cartoon illustration of what I think are two different ways in which galaxies are forming their morphologies according to the TNG 50 model, at least, right? So low density filaments conducive to forming not just prolates, but it seems like dispersion-dominated sort of spheroidal galaxies. Internal mechanisms then transform them into disks. And high-density filaments can help retain this disk structure by high vorticity accretion, which is caused in these high-density filaments. But these are all, these are all simulation predictions. Can we compare them? Can we or test them with real data, right? That's what we want to find out. And so that's what the rest of this talk will be about. So I'm going to focus on Roman. And as you may know, it has a high latitude wide area survey planned out, which will map huge areas of the sky. But what we're going to focus on is that little dark green part of that footprint, which is the high latitude wide area survey deep field. Okay, and so this has a survey area of a little bit above the TNG 100 volume, and it will provide you with deep photometry and deep GRISM spectroscopy. Nestled within it is an ultra-deep tier which is a little bit above the TNG 50 survey area, and it has deeper photometry, but not deeper spectroscopy. Okay, so why do we need spectroscopy? Why is that important? Because you need spectroscopic redshifts to get you accurate 3D locations that you need in order to get accurate cosmic web maps, which you then use to test out these predictions, right? So what kind of samples would this give us? This is an example showing completeness fractions with stellar mass and star formation rate for 2 different Mach samples in TNG 100, right? The black line shows the sample with just photometry alone. And so the photometric sample is great. It's very complete in mass and star formation rate. The magenta line, though, troublingly, is a sample where you satisfy both photometric and spectroscopic limits. So this corresponds to a certain emission line flux limits, with which you can select galaxies to trace the cosmic web. And you can see that this is actually pretty incomplete. It only picks out the most massive and the most highly star-forming galaxies, which are rare in the universe. And this actually has a very devastating effect on the cosmic web structure that you would identify. Shown here is a visual comparison of the cosmic web in TNG 100 at redshift 1 from the full mass complete sample of all galaxies above 10 to the 8 on the right, and from this Mach sample satisfying the deep field photometry and spectroscopic limits on the left, right? And the dark matter overdensity is underlying the filaments, which are curves that are colored by how dense they are. You can see that on the left here, so from the Mach sample, you're missing a lot of stuff. You're missing real filaments, which trace sort of matter. What was that? Sorry, yes, on your right, yes. On your right, you're missing real filaments with corresponding to high overdensities, and you're identifying spurious filaments, which are just due to the biased tracers. So what do? One solution is to go deeper in spectroscopy, right? So you can do this over a smaller field of view. This is for TNG 50. Here you'll see the blue and the brown curves, which correspond to 5 and 2.5 times deeper spectroscopic limits, right? So going to smaller emission line flux limits, and you can see that with these deeper spectroscopic samples, you'll get more complete tracers of the cosmic web, going down to lower mass and star formation, and this will help you identify a more complete structure of the cosmic web, right? So this again is a comparison similar to before, but now you're looking at the full sample versus the 2.5 times deep and 5 times deep spectroscopic sample. So great, all you need to do is just do really deep spectroscopy, right? The problem is this is really, really expensive, right? As most of us will probably know, spectroscopy is expensive, and going this much deeper over just the ultra deep field will cost you hundreds, if not thousands of hours of Roman time. I don't think any TAC will give us that, right? So one solution to this is doing targeted spectroscopy, targeted deep spectroscopy over specific regions of the sky that you identify with the deep field. Deep field can give you, will show you the galaxy overdensities, and you can point Roman, or your telescope of choice, to those regions. And shown here in green is the Roman Wide Field Instruments field of view. You can do a few of these pointings to get deep spectroscopy in your regions of interest. Over smaller survey areas, you can do even better. It's even less expensive, and this is, I think, a viable way forward if you want to reconstruct the cosmic web at redshifts 1 and above. Okay, so I will leave a summary or coda of my talk here, and I'll just highlight a couple of ongoing projects we're doing that are relevant. And one of them, we're using JWST and IRIS data to identify to assess if accretion from the cosmic web can produce clumpy morphologies at cosmic noon. And finally, please see Joanna Wu's talk a little bit later to understand if the cosmic web can form sort of blue-centered compact galaxies. So thank you, and I'll take questions.
We have time for one quick question.
slime mold method is actually better than the disperse in identifying the filaments, but what is like a proxy or parameter that you can use to say quantitatively that it's actually better? How do you say it's better? Yes.
Yeah. So, I mean, we basically did, we correlated the density fields. Really what's better is the density field. Disperse uses Jelani tessellation, which is not very good for low density regions. Slime mold does better in low density regions, and you see a better correlation with the dark matter density field, which we have in the simulations.